Where are you right now? Not in the sense of the address on your mailbox or the GPS coordinates your phone could whisper. I mean, where are you? What is the shape of the room around you, the shadows it's holding? What time is it in your corner of the world? And if you're lying in bed, can you feel how the night has wrapped itself around you, like a heavy, patient ocean? Somewhere out there, far beyond the walls, the ground you think is still is moving. You're on a planet spinning at more than 1,000 miles an hour at the equator. That planet is also hurling around the sun at 67,000 miles an hour. And the sun itself is drifting through the Milky Way on a grand, slow arc that takes hundreds of millions of years to complete. Yet, you don't feel it. To you, the glass of water on your nightstand doesn't ripple. The air doesn't scream past your ears. Instead, it's quiet, still. So here's the question, one that's older than science, older than history. Is motion real, or is it just your brain stitching stillness into a story? If everything is always moving, maybe nothing is. Or maybe motion is only something that lives inside us, like a trick of the eye, a hum in the mind. Tonight, we'll wander slowly through the layers of that question. We'll start with what we think movement is, the easy, everyday version, the one we don't even notice ourselves believing. But before we can peel back that surface, we need to go back, way back. If you asked most people what movement is, they'd probably point to something obvious. A hand waving, a bird lifting from a branch, a car passing on the street. We think of movement as a change in position. You were here. Now you're there. The thing in between, the traveling from here to there, that's movement. It's simple enough that we teach it to children with arrows drawn on paper. We picture a little stick figure walking along a line from point A to point B. And because the idea feels so straightforward, we hardly ever stop to notice the hidden assumptions sitting inside it. We assume that space is just there, a kind of invisible stage on which everything plays out. That stage stays still, and movement is what happens when an actor, whether a human, a planet, or a falling apple, crosses the boards. We also assume that time itself is silently ticking along in the background. 1 second follows another, and in that steady rhythm, things shift. One moment you're leaning on the kitchen counter, the next you've walked to the fridge. It feels obvious because it matches our senses. Our eyes tell us something has changed location. Our inner ear tells us our own body has shifted. And our memory, stitched together in neat little sequences, agrees. We trust that if we saw it, felt it, and remembered it, then it must have happened in exactly the way we think. This everyday view of movement is practical. It's good enough to let you catch a ball, pour coffee without spilling, or drive through traffic without catastrophe. It's the kind of working definition we use without even realizing we're using it. But hidden inside that simplicity are a few silent rules that we've all accepted without much examination. There is a fixed background, something unmoving to measure movement against. Time flows at the same rate everywhere. A second for you is a second for me. Objects have exact positions. If you could freeze time, you could point to where something is without doubt. These rules feel so unshakable that we rarely even phrase them out loud. They're part of the quiet furniture of our thinking. But the cracks start to show when you push the idea just a little further. The illusion of being still. Imagine sitting on a train that's perfectly smooth and silent. You look out the window and see another train next to you. For a moment, you can't tell if your train is moving or theirs. The only way you can decide is by finding some fixed background. A tree, a building, the horizon. And if that fixed background isn't there, you're stuck in uncertainty. Our sense of motion always depends on a reference point. Take away that reference point, and movement starts to dissolve into guesswork. Now imagine that every possible reference point is also moving. The ground beneath your feet is spinning with Earth. The Earth itself is swinging around the Sun. The Sun is orbiting the center of the galaxy, and the galaxy is drifting through the cosmos. There is no absolute, unmoving background. Everything is in motion relative to something else. If that's true, then is anything really moving? Or is everything just changing its relationship to everything else? The problem with exact positions. In our day-to-day lives, we imagine that if you froze the world at any instant, you could pinpoint exactly where something is. Your coffee mug is on the table. The cat is on the windowsill. You are lying in bed, listening to this. But even this simple picture starts to warp under closer inspection. At the microscopic level, atoms are never truly still. Electrons swirl in fuzzy probability clouds rather than neat little orbits. Zoom in far enough, and position itself becomes slippery. An electron doesn't have one exact location until you try to measure it. This means that being somewhere isn't a straightforward fact. It's a matter of probabilities, tendencies, and chance. The time problem. We like to think of time as a perfectly even flow. Tick, tick, tick. But modern physics has shown that time can stretch or shrink depending on how fast you move or how strong gravity is where you are. Two people moving differently will experience different amounts of time passing. This means that even something as simple as movement takes time is more complicated than it first appears. If time isn't universal, then our nice clean diagram of an object moving from point A to point B in a set duration is more like a patchwork quilt of experiences, stitched together but not identical for everyone involved. Everyday contradictions. We think movement is obvious, and yet we constantly experience its contradictions. You sit in an airplane for hours, barely feeling like you're moving, but you've crossed continents. You spin in a circle on a playground as a child and feel dizzy, even though, to an outside observer, you stayed roughly in the same spot. You drift off to sleep on a road trip and wake up hundreds of miles away without any sense of having traveled at all. Sometimes, movement feels fast when it's slow, and slow when it's fast. Sometimes it feels smooth when it's actually chaotic, or chaotic when it's smooth. The reality of what's happening and the way we feel it happening are not always in perfect alignment. And so the tidy little definition we carry in our heads, movement is a change in position over time, begins to fray at the edges. We start to realize it's not a universal truth, but a kind of shorthand. A story we tell ourselves because it's useful, not necessarily because it's the deepest truth. So, if our everyday sense of movement is incomplete, if it's full of assumptions, shortcuts, and illusions, then what lies beneath it? To answer that, we need to travel back in time, not in the sci-fi sense of stepping into a machine, but in the gentler way of turning the pages of human understanding. Back to when motion was one of the great mysteries, and our ancestors were still arguing over what it even was, before Einstein, before Newton, before anyone had even thought to name gravity. Because to see where our modern ideas came from, we have to stand where humanity once stood, looking up at the sky, watching the stars, and wondering why some of them wander. Before there were satellites, before stopwatches, before we could measure anything with more than our eyes and the slow sweep of the seasons. There were the stars, and they told a story that seemed simple. Some stars stayed fixed in their patterns, tracing the same shapes across the night over and over. But others wandered. They shifted their position, night after night. The Greeks called them planetae, the wanderers. We call them planets. The first scientists weren't scientists at all. They were farmers, keeping track of planting seasons. Sailors navigating by constellations. Priests marking the holy days. They watched the heavens not because they wanted to prove a theory, but because their lives depended on it. In that ancient view, the earth was still. It had to be, because it felt still, and movement belonged to everything else. The sun moved across the sky, then the moon, then the planets, each on its own path. The heavens were in motion. We were the unmoving center, the Aristotelian world. By the 4th century BCE, Aristotle gave this everyday observation a grand, formal shape. To him, the earth was fixed and unmoving at the center of the universe. Around it were crystal spheres, each carrying the sun, moon, and planets in their perfect circular paths. Motion was natural to things. Objects sought their natural place. A rock fell because its natural place was the ground. Fire rose because its natural place was the heavens. In this view, there was no need for invisible forces, no mysterious pull between objects. Things simply moved because of their own essence, and once they were at rest in their proper place, they stayed there. It was elegant, it matched the senses, and for nearly 2,000 years, it was taken as truth. The clockwork shift. Then came the Renaissance, and with it, a quiet rebellion against the crystal spheres. Copernicus placed the sun, not the earth, at the center. It was a shocking idea, but it made certain calculations cleaner. Still, to most people, it felt absurd. After all, if the earth was spinning and orbiting, wouldn't we feel it? Wouldn't birds be blown backward when they took flight? Wouldn't loose stones roll away from us? It would take another century before those objections began to crumble. Galileo's experiments. In the early 1600s, Galileo Galilei began rolling balls down inclined planes. Not a very cosmic image, just wood planks, metal balls, and a patient man with a keen eye. But from these humble setups came a quiet revolution. Galileo noticed that once an object was moving, it tended to keep moving unless something slowed it down. The reason things stopped rolling wasn't because motion naturally died out. It was because friction and resistance stole their energy. Take away that resistance, and the motion would continue, forever. This was a crack in Aristotle's world. It suggested that rest wasn't the natural state of things. Uniform motion could be just as natural. Galileo also looked at the sky through a telescope. He saw moons circling Jupiter. If those moons could orbit a planet without flying off into the void, then maybe the Earth could orbit the Sun without losing its moon. It was the beginning of the end for the old idea of movement. Newton's laws. By the late 1600s, Isaac Newton brought all these threads together. His Principia Mathematica didn't just describe motion, it gave it rules. 3 rules, in fact, that seem to explain almost everything. An object in motion stays in motion unless acted on by an outside force. Motion, once begun, doesn't need a cause to keep going. It needs a cause to stop. Force equals mass times acceleration. Push harder, move faster. Heavier things resist change more than lighter ones. For every action, there is an equal and opposite reaction. Movement is a conversation. Push on the world, and it pushes back. Alongside these laws was Newton's great invisible player, gravity. No more natural place for rocks and fire. Instead, every bit of matter pulled on every other bit across any distance. The moon wasn't glued to the Earth by a sphere. It was falling around us, held in a kind of endless embrace by gravity's pull. For the first time, movement wasn't just a thing you could see, it was something you could predict. The heavens and the earth followed the same rules. You could calculate the swing of a pendulum and the path of a planet with the same equations. The universe became a clockwork, every gear meshing perfectly with the next. Why it felt so final. Newton's model was so successful that it didn't just work for the motions we could see, it predicted motions we hadn't seen yet. The discovery of Neptune, for example, came from noticing oddities in Uranus's orbit and calculating that another planet must be tugging on it. Mathematics pointed the way, and telescopes confirmed it. To most minds, that was it. Motion was explained. You could stop looking for mystery. And yet, even in Newton's time, there were strange little gaps, things that didn't quite fit. Mercury's orbit was slightly off from what Newton's equations predicted. Light, which everyone thought was made of particles, sometimes behaved like a wave. And if space was just a vast, unmoving stage, what was it made of? The ether that wasn't in the 1800s. Scientists imagined that space must be filled with a substance called the luminiferous ether. It was supposed to be the medium that light waves traveled through, like air for sound or water for ripples. This ether was the new background of movement, the fixed frame everything could be measured against. But when physicists tried to detect it in experiments, most famously in the Michelson-Morley experiment, it simply wasn't there. No matter how carefully they measured, the speed of light seemed to be the same in every direction, for every observer, no matter how they themselves were moving. It was as if the universe refused to give us a stationary backdrop. The Einstein disturbance. Then, in the early 20th century, Albert Einstein stepped in with his special theory of relativity. In it, there was no absolute space, no absolute time, only space-time, a woven fabric that could stretch, bend, and warp. Movement wasn't about shifting through a fixed stage. It was about moving through this flexible geometry. And here's the part that still feels like a magic trick. The faster you move, the slower time flows for you compared to someone standing still. Distances shrink along the direction of motion. And no matter how fast you go, the speed of light remains the same. Motion had become something deeply relative. What one person sees, another might not. There was no longer a single, universal story of what's moving and what's still. But as we looked deeper, Newton's laws still worked for everyday speeds and sizes. You can still calculate a baseball's path with them, or send a spacecraft to Mars. But in the realms of the very fast, the very massive, or the very small, the old laws begin to blur. Einstein gave us the strange truth of relativity. Quantum mechanics began to show us that particles don't have exact positions until they're observed. And suddenly, movement wasn't just a path through space. It was a shifting, uncertain dance between matter, energy, and the fabric of space-time itself. We had traded the crystal spheres for clockwork, and the clockwork for something far stranger. And now, movement wasn't simply about what's out there. It was also about what's in here, the mind that sees it. Because if motion depends on perspective, what happens when the perspective isn't perfect? If movement were only an external fact, an object sliding from here to there, it would be easy to pin down. But movement isn't just out there. It's also in here, in your head, your senses, your memory. And the strange thing is, the version your brain gives you is not the same as the one the universe might be telling. Your eyes don't see motion. This sounds impossible, but your eyes don't actually see movement. They see snapshots, frames of light and shadow, color and contrast. These frames arrive in little bursts, and your brain stitches them together, smoothing the jumps, creating the illusion of continuous flow. If you've ever seen a flipbook animation, you know the trick. Still images, one after another, become a running figure or a bird in flight. That's exactly what your nervous system does all the time. You are, in a way, always watching the flipbook version of reality. And just like a flipbook, sometimes the pages blur. Ever watch a spinning wheel in a movie and notice it looks like it's moving backward? That's your brain getting out of sync with the frames, a reminder that motion is as much an interpretation as it is a fact. The half-second delay. It gets stranger. Neuroscientists have found that your brain actually runs a little behind reality by about half a second. It waits for enough sensory information to arrive, then edits it into a smooth experience before serving it up to you as now. This means that what you feel as the present is already the past, gently polished by your mind. The world you're moving through is always a half-second old. You don't notice because your brain hides the stitching. It's like a skilled film editor removing all the jump cuts so the story flows. Motion without movement. You can feel movement without actually moving. Close your eyes and have someone slowly tilt the chair you're sitting in. You'll swear you're sliding forward even though you're not. Or think about the sensation when an escalator you expect to be moving is turned off. You step onto it, and for a split second, your body insists it's in motion. This comes from your vestibular system, the fluid-filled canals in your inner ear that sense balance and acceleration. When those signals don't match what your eyes are telling you, your brain scrambles to reconcile the difference, sometimes creating movement where there is none. Phantom motion. Have you ever been stopped at a red light and felt your car inching forward, only to realize it was the car next to you rolling back? Your brain doesn't always know which reference point to trust. It can decide you are the one moving, simply because of the way the scene shifts around you. The same trick is why IMAX movies can make you feel like you're flying, or why VR headsets can trigger motion sickness without your body moving an inch. Your brain believes movement if the right signals arrive in the right order. Reality itself is negotiable to your senses. The power of expectation. Our brains aren't just passive receivers, they predict. They constantly guess what's about to happen next, based on patterns from the past. If you toss a ball in the air, your brain starts calculating where and when it will land, adjusting your muscles before your eyes even finish tracking it. This predictive wiring is so strong that it can override raw sensory input. If the ball suddenly changes direction mid-air, thanks to a gust of wind, you'll feel a jolt of surprise. That jolt is your brain updating the story it had already started telling you. Editing your own past. One of the most unsettling parts of perception is that your brain sometimes rewrites history to make motion look smoother. In an experiment called the flash lag effect, a moving object and a flashing object appear at the same spot, but your brain places the moving one ahead of where it really was when the flash occurred. It's as if your brain is guessing the future and retroactively adjusting the past so everything lines up. In other words, part of what you think you saw may never have happened exactly that way. Why this matters? If your sense of movement depends on stitching, smoothing, and predicting, then motion isn't just about objects in space. It's about you, the observer, turning raw changes into a coherent story. That means two people could see the same event and experience very different movement. A runner on a track may feel like the race passed in a blur, while a spectator may feel it unfolded in slow, clear detail. A driver swerving to avoid a deer might later swear the animal leapt faster than was possible because adrenaline slowed the brain's internal clock. The perception illusion. Now imagine zooming in past the human scale, down to the level of molecules, atoms, and particles. At that level, motion looks even stranger. Particles pop in and out of existence. Their positions smear into probability waves. They don't have neat paths from point A to point B. They exist in a haze until measured. The mind wants motion to be smooth, like a ribbon drifting in water. But underneath, it's jagged, uncertain, and sometimes discontinuous. We never see that raw truth. We see the version our brains can live with. So maybe movement isn't just what happens out there in the world. Maybe it's also something happening in the mind, a constructed sense of continuity, built out of scattered frames, delayed signals, and constant predictions. And if that's the case, we have to wonder, if motion gets this strange at the scale of human senses, what happens if we shrink ourselves further? What happens when we enter the realm of the tiny and the weird, where particles refuse to play by our rules? We've already seen how movement gets slippery when filtered through the human mind. But the mind isn't the only thing that reshapes motion. The universe itself does. And if you keep zooming in, past skin, past cells, past molecules, all the way down to the level of atoms and the particles within them, movement begins to lose its familiar shape entirely. A world without paths. At our everyday scale, movement is like a line. You go from here to there. It might curve, it might loop, but it's still a single, clear path. At the quantum scale, that picture collapses. Particles don't follow neat tracks through space. Instead, they exist in a cloud of possibilities, a haze of where they might be, each location weighted by probability. In the famous double-slit experiment, a single electron fired toward two slits doesn't pick one or the other. It behaves as if it has taken both paths at once, interfering with itself like a wave. Only when you measure it, force it to choose, does it act like it traveled one definite route. It's as though movement isn't something a particle does. It's something that emerges when we look. The dance of superposition. Superposition is the unsettling quantum fact that a particle can exist in multiple states at once until observed. An electron can be spinning both clockwise and counterclockwise. A photon can be traveling multiple paths. If you think of motion as being in one place, then another, superposition laughs in your face. Here, a particle can be in all the places it might be simultaneously without committing to any of them. In this sense, quantum motion isn't like a runner crossing a finish line. It's like a whisper of possibilities hanging in the air, waiting to condense into a single outcome. The uncertainty principle. Heisenberg's uncertainty principle tells us you can't know both a particle's position and its momentum with perfect accuracy. The more precisely you know where it is, the less precisely you can know how fast it's moving, or even if it's moving at all. This isn't about bad measuring tools. It's a built-in feature of reality. At this scale, movement stops being a crisp line and becomes a blur between knowing where something is and how it's going. It's like trying to track a bird in thick fog. You can either find the exact branch it's perched on or catch a glimpse of its flight, but not both at the same time. Particles that refuse to let go. Then there's entanglement, the eerie bond where two particles become linked so that what happens to one instantly affects the other, no matter how far apart they are. In a way, this breaks our idea of motion entirely. If two entangled particles can share information instantly, faster than light, then movement isn't the only way for change to travel. Somehow, the state of one particle can jump across space without crossing the space in between. It's not movement. It's something deeper, stranger, connection without travel. Vacuum that's not empty. Even empty space isn't truly empty. Quantum field theory tells us that the vacuum is alive with energy. Tiny, fleeting particle-antiparticle pairs constantly appearing and disappearing. This restless sea of fluctuations means there's no true stillness, even in perfect darkness. If the vacuum itself is always in motion, then movement is not just a property of objects, it's baked into the fabric of existence. Stillness, in the deepest sense, might not even exist. Why this feels so alien? At the human scale, we trust our senses. If we can see something moving, we believe it moved. But at the quantum level, seeing changes the thing you're looking at. An unmeasured particle doesn't have a defined path. The act of observing creates the reality you witness. That means motion at the tiniest scales is not an absolute fact. It's a kind of co-creation between the universe and the observer. The beauty in the chaos. It's tempting to think of all this as cold or alien, but there's a strange beauty here. Quantum motion isn't rigid. It's fluid, playful, full of possibilities. It's the hum of a hidden ocean beneath the floorboards of our reality. You are, at this very moment, made of particles that refuse to stay still. The atoms in your hand are buzzing with energy, their electrons smeared into shimmering clouds, their nuclei vibrating with restless precision. You are a body of motion, even when you think you're at rest. The scale problem. So, we have this puzzle. At the smallest scales, movement is fuzzy, probabilistic, and deeply dependent on observation. At the human scale, it's solid, predictable, and apparently independent of who's watching. How do these two realities connect? That's one of the deep mysteries of physics. How the strange quantum rules collapse into the stable everyday world we live in. And no one has fully solved it. But if the small is strange, what about the large? If the tiniest movements are hidden in quantum haze, what does movement look like when we zoom out far enough to see galaxies, clusters, and the fabric of space-time itself? Because if the small hums with mystery, the vast drifts in an entirely different kind of wonder. If the tiny world is restless and uncertain, the vast world feels deliberate, slow, like a breath held for billions of years. And yet, at this largest scale, movement is everywhere. It is written into the structure of the cosmos itself, so large, so constant, that we forget it's there. The planet beneath you, right now, wherever you are, the ground feels still. The bed, the chair, the floorboards, they all seem unmoving. But this is only because you're moving with them. The Earth is spinning at over 1,000 miles per hour at the equator. It completes one rotation every 24 hours, carrying you effortlessly along for the ride. This spin is so steady, so smooth, that it disappears from awareness. Like the hum of a refrigerator, you only notice when it stops. But that's only the first layer. Our spinning Earth is also orbiting the Sun at 67,000 miles per hour. The Sun itself orbits the center of the Milky Way at about 514,000 miles per hour. And the Milky Way is moving toward the Andromeda Galaxy at 252,000 miles per hour. You are never still, not for a second. The shape of orbits. At our human scale, we picture movement as straight lines, but in space, almost nothing moves straight. Gravity bends paths into curves, ellipses, spirals, arcs. Planets circle stars. Stars circle galactic centers. Galaxies circle within clusters. Every curve is a compromise between falling and moving forward. If Earth stopped moving forward in its orbit, we'd fall into the sun. If we moved too fast, we'd slingshot away into the dark. Our whole planet is suspended in this perfect tension, a movement that's also a constant fall. The expanding stage. For centuries, scientists thought the universe was static. But in the 1920s, Edwin Hubble measured the light from distant galaxies and found they were all moving away from us. Not because we're special, but because space itself is expanding. This expansion isn't like explosions in air. It's more like dots on the surface of a balloon as it inflates. Every dot moves away from every other dot as the space between them grows. This means the stage for movement, the backdrop we thought was fixed, is itself in motion. And here's the mind-bender. There is no center to this expansion. Every point is the center from its own perspective. Light on the move. Even light, which feels instantaneous to us, is constantly traveling. From the sun to your eyes, light takes about 8 minutes. From the nearest star, 4 years. From the Andromeda galaxy, 2.5 million years. When you look at the night sky, you are seeing ancient motion, photons that have been crossing space since long before human beings existed. Some of the stars you see may no longer even be there. You are watching the footprints of movement long after the traveler has gone. Galaxies in the dark. The galaxies themselves are not only moving through space, they are being tugged and twisted by the invisible gravity of dark matter. This unseen mass shapes the cosmic web, the great structure of the universe, vast filaments of galaxies, separated by even vaster voids. On this scale, movement is like the slow shifting of continents, but multiplied 1,000,000 times over. Clusters drift, filaments stretch, voids grow emptier. If you could speed up billions of years into a minute, the universe would look like a living organism. Threads pulling, knots tightening, space itself breathing. The longest falls. Black holes add their own drama to cosmic motion. Anything straying too close is pulled inward, falling forever toward the event horizon. From far away, it looks like the falling object slows, red shifting until it fades from sight. But from its own perspective, it plunges in quickly, swallowed into the singularity. In a way, this is the ultimate one-way movement, a journey that ends in a place that is not a place, where space and time themselves break down. Cosmic drift. Even galaxies, the grandest islands of stars, are temporary things. The Milky Way and Andromeda are on a slow-motion collision course, set to merge in about 4 billion years. When they meet, their stars will mostly pass each other in the vast, empty spaces, but their mutual gravity will reshape them into a single, larger galaxy. In the deep future, the night sky will change completely. The constellations we know will vanish. A new set of cosmic landmarks will define the heavens. Movement, even at this scale, is not a gentle backdrop. It's the sculptor of history. When the cosmic clock runs out, the universe is not just expanding, it's accelerating. Dark energy, another invisible player, is pushing galaxies apart faster and faster. In the unimaginably distant future, the galaxies beyond our local group will slip away faster than light can reach us. Their motion will carry them out of view forever, leaving our corner of the cosmos isolated. One day, movement itself will erase the evidence that there was ever a larger universe beyond our own cluster. The mirror of the tiny strangely, the vast and the tiny share something. In both, there's no absolute stillness. Particles hum with quantum restlessness. Galaxies drift through expanding space. The scales are different, but the lesson is the same. Everything moves, always, even when it feels still. And here's where the cosmic view begins to bend back toward the unsettling. If motion is everywhere, and the stage itself is shifting, then maybe our whole idea of movement is just another layer of the story we tell ourselves, which leads to a possibility both thrilling and dizzying. What if none of it is truly real? We've traced motion, from the familiar to the strange, from the scale of electrons to the sweep of galaxies. And at every level, it's been a little slippery, never quite as solid as it first appears. So here's the question that sits at the edge of the bed tonight, waiting for you to look it in the eye. What if movement isn't real at all? Not in the way we think, not as some universal fact, but as a story stitched together in the mind. The dream possibility. Think of the last vivid dream you had. You walked through rooms, ran down streets, maybe even flew. In that dream, you felt movement, your heart racing, the air rushing by, the ground shifting beneath you, but your body never left the bed. If a dream can create movement without actual travel, could waking life do the same? Could motion be a kind of waking dream, a convincing simulation running in the theater of consciousness? The simulation hypothesis. Some philosophers and scientists have taken this idea seriously. The simulation hypothesis suggests that our reality could be a highly sophisticated virtual environment, like a cosmic computer program. If that's the case, motion might be no more fundamental than the shifting images on your phone screen. In a video game, your character can sprint across a field or sail through the air, but in the code, nothing is actually moving. The game simply redraws the scene, frame by frame, in a way that feels like motion to the player. If our universe works the same way, movement could be an illusion born from rapid changes in information, a rendering trick of the cosmos. The brain in a vat thought. Long before the language of simulations, philosophers imagined a simpler version, the brain in a vat. If a brain were kept alive and fed perfect electrical signals, it could believe it was walking through a park, feeling the sun, hearing the birds. The motion would feel real, but there would be no park, no walking, no real change in position, just signals interpreted as movement. And here's the uncomfortable truth. From inside the experience, you can't be sure you're not in such a setup right now. The only evidence you have of motion comes from your senses, and we've already seen how easily those can be fooled. Consciousness first models. Some interpretations of physics and philosophy go even further. They suggest that consciousness, not matter, is the fundamental reality. In this view, the universe isn't a machine that happens to produce awareness. It's a field of awareness that happens to produce the illusion of machines. If awareness is primary, then everything we experience, space, time, and movement included, might be patterns arising within mind itself. Motion wouldn't be something out there at all. It would be a change in the arrangement of experiences, like shifting colors in a kaleidoscope. What happens to here and there? If movement is an illusion, then the concepts of here and there also start to blur. In a dream, you can be on a mountaintop one moment and in a city street the next, without any in-between. If waking life operates the same way under the hood, then travel could just be a rearrangement of what's being displayed to consciousness, no journey required. In such a reality, motion isn't a fact of physics, it's a style of storytelling. Why this doesn't feel like an illusion? The trouble is, the illusion is perfect. Even if reality were simulated or consciousness-based, the movement we experience comes with all the sensory richness of real motion. Your inner ear tilts when you lean, your muscles tense as you run, your eyes track shifting scenery. Every sense agrees, and so the story holds. But perfect illusions are still illusions. The sun feels like it's moving across the sky, but we know it's the earth that turns. Your breath feels still in your chest when you lie in bed, but the molecules in it are in ceaseless motion. Feeling is not always fact. The soft paradox. So maybe motion isn't real, or maybe it is, but only as a relational thing. Something that exists between events, not as a standalone truth. In that case, asking, is it real, might be like asking if a shadow is real. Yes, it exists as long as there's light and an object to cast it. But no, it has no substance of its own. Motion might be the shadow cast by change, and change, in turn, might be the shadow cast by something even deeper, something the mind can't yet name. We could stop here, float in this philosophical fog, and call it a night. But there's another step, the place where science, philosophy, and mystery meet. Because even if movement is an illusion, there are still pieces missing in our understanding. Puzzles that neither physics nor metaphysics can quite solve. And it's in those gaps, in the mystery, that the story gets even stranger. By now, movement feels less like a solid thing you can grab, and more like a ghost that keeps changing shape when you try to hold it. We've seen it shrink into quantum haze. We've seen it stretch across the cosmos. We've watched it dissolve in the light of philosophical doubt. And yet, even with centuries of thought, there are places where our understanding simply runs out of road. The edges of the map are still drawn with clouded ink. The frame problem. If motion is relative, we still have to ask, relative to what? Einstein showed us that there's no absolute rest in the universe, only motion compared to something else. But if everything is moving, is there a master frame, a hidden reference point the cosmos is secretly measured against? Some experiments, like those looking at the cosmic microwave background, the faint afterglow of the Big Bang, suggest we can measure motion relative to that ancient light. But whether that counts as a true background or just another moving part is still a matter of debate. The nature of time movement is always tied to time. 1 second you're here, the next you're there, so time feels like the thread on which the beads of motion are strung. But physics hasn't settled on what time actually is. In some equations, time is just another dimension, no different from space. In others, it emerges only when change happens, meaning that if nothing moved, time itself might not exist. If time is slippery, then motion, its dance partner, can't be much more certain. The quantum classical divide. At the smallest scales, particles behave in ways that seem to ignore the rules of motion we see in daily life. At larger scales, those quantum oddities somehow average out into predictable, classical movement. But how exactly does that transition happen? We call it the measurement problem. But the truth is, we don't fully understand why our macroscopic world looks so stable when its building blocks are so wild. The energy puzzle movement requires energy, or at least that's what we've always thought. A rolling ball slows when friction saps its energy. A spaceship needs fuel to accelerate. But in deep space, without friction, a moving object keeps going forever without needing new energy. It's as if the universe allows pure motion to exist without cost, so long as nothing interferes. And then there's dark energy, which seems to be accelerating the expansion of the universe itself. If movement needs a cause, what's pushing the galaxies apart? We don't know. The problem of the observer. At the quantum level, observing something changes it. But does this apply to motion itself? If you measure a particle's position at 2 different times, you'll see that it has moved. But in between those measurements, was it actually moving? Or was it existing in a series of disconnected states that only form a path when observed? It's a question with no final answer. At least, not yet. The illusion we can't shake. Even knowing all this, we still feel motion in our bones. The tilt in an airplane as it banks. The slow sway of a dock underfoot. The lurch in your stomach when a roller coaster drops. Those sensations are so convincing that they override intellectual doubt. You might know the Earth is spinning at 1,000 miles an hour, but you'll never feel it. You might suspect that quantum particles are just probability clouds, but you'll always see the baseball's clear arc as it sails through the air. We live in the story of movement because it's the only story our senses can tell. Letting the mystery breathe. It's tempting to rush toward answers, to declare that motion is either real or not real, physical or illusory. But maybe the more interesting choice is to stop at the edge, look out into the fog, and let the question hang there. Because motion is not just a problem for physicists, it's a piece of poetry. It's the reason rivers exist, the reason music has rhythm, the reason seasons turn. It's the difference between a photograph and a film. It's the heartbeat of change itself. Even if we never find the missing pieces, we still live with movement every day. We carry it in our muscles, our breath, our pulse. It is stitched into the smallest actions of our bodies. And maybe, to understand it more deeply, we don't need to look only at stars or electrons. Maybe we should turn inward to see how motion lives inside us, how our bodies have their own private relationship with it, one we can feel without any telescope or particle accelerator at all. We've followed movement through galaxies, through atoms, through thought experiments and theories. But all of that still feels out there, somewhere in the distance. What about the movement that is closest of all? The motion that happens quietly, without your permission, even while you sleep. The movement that you are. The constant motion of being alive. Even when you lie perfectly still, your body is in ceaseless motion. Your heart is beating, pushing waves of blood through arteries and veins. Your lungs are expanding and contracting, trading carbon dioxide for oxygen. Your stomach muscles are shifting food along. Your cells are dividing. Your neurons are firing tiny electrical signals. Every moment, trillions of microscopic processes are unfolding. Ions sliding through channels, proteins folding into shape, DNA unzipping and copying itself. If you could see yourself at that scale, you would look like a galaxy of swirling, shimmering events. Stillness, in the biological sense, doesn't exist. The private ocean, inside you, your body is about 60% water, and that water is never still. Blood flows, lymph drifts, even the fluid in your inner ear, your vestibular system, is always shifting, helping you balance. Those inner tides are part of why motion feels so instinctive to us. We don't just see it in the world, we feel it from the inside out. When you sway, your inner ocean sways with you. When you spin, it sloshes in spirals, sending your brain signals about where you are in space. The breath clock. Breathing is movement's most faithful companion. Each inhale pulls the world in. Each exhale lets it go. It is the rhythm that underlies all the others, the silent metronome of life. When you walk, your breath changes to match the pace. When you run, it quickens. When you rest, it slows, and you can almost feel the world breathing with you. Some meditation traditions use breath as a way to dissolve the illusion of separation between body and world, because in breathing, you are literally trading matter with the air around you. The border between you and not you becomes more porous than it seems. Circadian motion. Your body doesn't just move in space, it moves in time. Every cell carries a clock, ticking with the rhythm of day and night. These circadian rhythms guide your sleep, your temperature, your hormones. You are, in a sense, riding a wave of time each day, cresting at wakefulness, dipping into rest. Movement here is not about going somewhere. It's about cycling through states, like the phases of the moon. Your body is a planet with its own seasons. Motion. You can hear. If you put a stethoscope to your chest, you can hear the constant thump of your heart. If you listen even more closely, microscopically, you would hear the whir of mitochondria generating energy, the buzz of synapses firing, the shuffle of molecules. In a way, your body is an orchestra of movements, playing a piece you never consciously composed. You are both the music and the listener. When the inner motion falters, we often only notice our body's movement when it changes unexpectedly. The dizzy sway when your inner ear misfires, the racing pulse in moments of fear, the sluggishness when illness slows everything down. These moments remind us how much of our sense of stability depends on hidden motions we can't control. When the inner dance falters, the whole world feels off balance. Why it feels so intimate. There's a difference between watching the wind move the trees and feeling your own heartbeat. One is motion you observe, the other is motion you inhabit. You can be a passive witness to the cosmos spinning, but you are an active participant in your own body's movement. And in that participation, motion becomes something more than physics. It becomes life itself, the quiet link to time. Think about how we measure time. By motion, the swing of a pendulum, the vibration of a cesium atom, the turning of the earth, the beating of a heart. Even your own awareness of time passing is rooted in movement, of hands on a clock, of light shifting through the day, of your own breath and pulse marking moments. If all motion stopped, time would be meaningless. Without the gentle push of change, there would be nothing to measure, from the body to the story. And so movement is not just out there in the stars, or down there in the particles, it is also in here, in your body, woven into the intimate moments of living. It is in the way your breath moves your chest as you fall asleep. It is in the way your heartbeat changes when you hear your name spoken softly. It is in the tiny shifts of your eyes as you read these words, even now. And perhaps it's in this everyday private relationship with movement that the mystery feels most tangible. Because here, you can both feel it and be it. But if movement is this deeper part of us, it makes you wonder, how long have we been trying to understand it? How many centuries have humans been watching rivers flow, stars drift, animals run, and wondering what exactly is happening? To answer that, we'll have to turn the clock backward again. This time, not to the birth of modern physics, but to the long, winding human story of trying to grasp what motion really is. Before equations and telescopes, before philosophy was written down, there were just people watching rivers slide past their banks, watching clouds crawl across the sky, watching the sun climb and fall, the moon wax and wane. Movement was one of the first mysteries. It was everywhere, but it was never the same twice. It could be gentle or violent, predictable or chaotic. And so, like all great mysteries, it became a story, the myths of the moving world. In some ancient cultures, the wind was thought to be the breath of a god. The tides were the pull of a sea deity's hand. The stars were lamps carried by celestial beings walking an invisible path. For the Maori of New Zealand, the sun's movement was once explained as the sun being too fast, until the hero, Maui, slowed it down by catching it in ropes. For the Norse, The sun and moon were chased across the sky by wolves, and their motion was the desperate flight to avoid being caught. Movement was not yet a law. It was an act of will, of personality. Things moved because someone or something made them move. The first measurements. By the time of the Babylonians and ancient Egyptians, movement had become something to track. The rising of Sirius in the dawn sky marked the coming floods of the Nile. The positions of planets predicted seasons, planting times, even the fate of kings. The Greeks refined this watching into geometry and logic. Eratosthenes measured the Earth's circumference by comparing shadows at noon. Hipparchus mapped the stars and noticed that their positions shifted slightly over centuries, a slow drift we now call precession. For the first time, motion was not just observed. It was measured, predicted, and written down. Aristotle's rules. Aristotle gave the ancient world its first big framework for motion. He split it into two kinds: natural motion, like stones falling or smoke rising, which happened without force; violent motion, like pushing a cart, which required effort to maintain. It fit what people saw. If you stop pushing the cart, it stops moving. And so, for almost 2,000 years, his model held. The sky as a machine. In the Islamic Golden Age, scholars like Ibn al-Haytham and al-Biruni began questioning old assumptions. They refined astronomical measurements, developed early theories of inertia, and experimented with optics, how light itself moved. Meanwhile, in medieval Europe, thinkers like Jean Buridan proposed that motion could continue without constant force, an idea that would echo in Galileo's later work. The more people looked, the more cracks they found in Aristotle's picture. The great shift by the Renaissance. New tools made new truths visible. Galileo's telescope revealed moons orbiting Jupiter, proof that not everything moved around Earth. Kepler studied the paths of planets and found they moved in ellipses, not perfect circles. Newton gathered all these scattered threads into his laws of motion and gravity. For the first time, motion wasn't just described, it was unified. Apples fell and planets orbited for the same reason, an invisible force pulling them together. The universe became a great clock, ticking with perfect regularity. When the clock broke for 2 centuries, Newton's clockwork seemed flawless. But in the late 1800s, light refused to behave according to the old rules. And at the smallest scales, atoms and particles didn't move in predictable ways. Einstein replaced the clock with a fabric, space-time itself, bending and stretching. Quantum physics replaced the clean paths of particles with probability clouds. The human story of motion had shifted again, from myth to measurement to laws to uncertainty. Why this story matters. Every step in this long history was shaped by what people could see and measure. And each time we thought we had the answer, the horizon moved. New tools revealed new truths. New truths revealed new mysteries. And that's the real shape of the story. Movement has never just been about things changing place. It has always been about us, changing our minds about what movement is. Which leaves one more question, the question that might be the strangest of all. After thousands of years of watching, measuring, and explaining, what if movement doesn't actually exist in the way we imagine? We've built motion into the bones of our understanding. It's how we tell time, how we explain change, how we imagine the unfolding of the universe itself. But what if motion is only a trick of perspective? What if it doesn't exist the way we think it does, or at all? The relativity of stillness. Think about sitting on a moving train. The seat under you feels still. Your coffee cup isn't sliding across the table. And yet, you're hurtling across the countryside at 80 miles an hour. From your perspective, you're at rest. From the perspective of someone standing by the tracks, you're moving. Which one is true? Einstein's answer was that neither is absolute. Motion only exists relative to something else. That means there is no universal moving or still. There are only relationships. If motion only exists in comparison, can we call it real in itself? The quantum mirage. At the smallest scales, the problem gets worse. Particles don't have definite positions or paths until measured. In between, they exist in a haze of probabilities. So, is a particle moving through that haze? Or does moving only make sense once we force it into a single, measurable outcome? In this view, motion might be like a mirage on a hot road, convincing from a distance, but gone when you try to touch it. Change without travel. Some physicists suggest the universe is made of discrete states, like individual frames in a film reel. In that case, motion isn't a continuous flow. It's the rapid switching from one state to another, with our minds smoothing the gaps. There's no actual moving, just a sequence of different nows. It's unsettling to imagine that the space between those frames might be nothing at all. Emergent illusions. Philosophers sometimes call motion emergent, not fundamental, but a side effect of deeper rules. Like how heat is not a basic property of reality, it's what we call the collective motion of particles. Maybe motion itself is just our name for a pattern we perceive when changes line up in a certain way. In that case, movement would be like a rainbow, real enough to see, but dependent on the angle of the observer. Change the angle, and the rainbow, and perhaps the motion, disappears. The brain's hand in it. We've already seen how the brain constructs motion from snapshots, edits the timeline, and predicts what comes next. If the experience of movement can be created or altered in the mind, how much of it belongs to the external world at all? Maybe motion isn't a property of matter. Maybe it's a property of perception, a way for consciousness to organize the chaos into something livable. Why this doesn't break the world? If motion were an illusion, daily life would still work. You could still catch a bus, pour tea, and orbit the sun, because the illusion is consistent. It behaves as if it were real. In fact, we already live with illusions like this. The solidity of a table is an illusion. The atoms are mostly empty space. Color is an illusion. Light itself has no color until your brain interprets its wavelength. Yet we rely on these illusions every day. Motion could be the same. Not fundamentally there, but experientially unavoidable. A quiet acceptance. If we let go of motion as an absolute, we lose a kind of certainty, but we gain something else. We start to see that movement, like time, like space, is part of a web of relationships. It's not a thing. It's a connection, not an object. It's an arrangement of changes, stitched together by the observer. And maybe that's enough. Maybe motion doesn't have to be real, in the ultimate sense, to be real enough to live by. Whatever it is, or isn't, we've traveled far tonight. From the smallest tremors of quantum fields to the slow drift of galaxies. From ancient myths to the frontiers of physics. From the rhythms of the body to the possibility that nothing really moves at all. All that's left now is to come back to where we began. To the quiet room you're in, the present moment, and the steady stillness that might only be another form of motion. Where are you now? Not in the grand cosmic sense, just here, in this moment. Maybe you're lying in bed, the blankets shaped softly around you. Maybe there's a small light in the corner, or just the quiet glow of your screen fading into the dark. Outside, the world has its own slow movements. Wind brushing the trees, the faint hum of distant cars. the silent spin of the earth under your feet. And yet, from where you are, it feels still as it felt when we began. The circle we've drawn, we've wandered far together tonight, through the easy, everyday sense of movement, through Newton's clockwork and Einstein's relativity, through the strange games your brain plays, the restless buzz of the quantum and the silent drift of galaxies, through the unsettling thought that motion might not exist at all, except in the way we tell the story. And somehow, after all that distance, we've come back to where we started. You, here, now, the stillness that moves. Maybe this is the quiet truth. You can be still and still be moving. The room can be still and still be moving. The planet can be still and still be moving. Because still and moving aren't opposites, they're the same thing, seen from different seats in the theater. And perhaps that's the gift of motion. Not that it carries you from one place to another, but that it lets you feel the thread that connects every here and now you've ever been. The last breath of the night. So let it all fall away now. The theories, the questions, even the mystery. Notice the gentle lift of your chest as you breathe in, the easy fall as you breathe out. That small rhythm is enough. It is the simplest movement, and in its simplicity, it contains the whole universe. Because whatever motion is, illusion or fact, shadow or substance, it has carried you here, to this moment. Breathing softly, still awake, still dreaming.